Dear academicians and researchers, ladies and gentlemen, I am Artem Chamili from the Department of Cybersecurity in Istanbul Commerce University at Istanbul, Turkey, and it's my pleasure to be part of the 10th annual IEEE conference on computational science and computational intelligence held in Las Vegas, Nevada, United States. I'll be presenting my paper titled Covert, Secure, and Private Communications in Software-Defined Networking. The scope of the problem, namely, since the days of ARPANET, the predecessor of the modern-day internet, communication privacy and anonymity were a matter of concerns. While there have been dozens of schemes proposed which deal with them, unfortunately, all of them have one or more drawbacks which are not suitable for the modern-day world. Namely, in private communications, the communicating parties and hosts hide their sensitive data, which is mostly application data payload, but they do not hide the fact that they are communicating, or they do not hide the forwarding informations and headers of the TCP IP protocol suite, such as IP, MAC addresses, TCP UDP ports, and so on. On the other hand, in the last decade or so, software-defined networking is being widely used when forwarding or even routing from end-to-end packets. And while doing so, SDN uses source and destination IP addresses, source and destination TCP UDP ports, source and destination MAC addresses, and so on. However, if you disclose the IP address of a certain host, you know its geographical locations roughly. If you know its UDP port that it's using, you know the application in that host. And if you disclose the MAC address of a certain host, you know exactly about which host we're talking about in the local area network. And thus, disclosing such information is undesired in the modern day world. That's why we need covert or anonymous communications, where all of those fields, headers, basically are hidden from the outside world. To this end, this paper proposes, improves, and adopts a few security building blocks. On top of them, we proposed a couple of covert, secure, and private communication protocols that outperform the current ones in terms of security and privacy characteristics. Also, we proved the security of the proposed protocols and experimentally show their computation and communication efficiency. This table basically summarizes and compares the proposed two secure routing or forwarding protocols with some of the related schemes among different covert security and privacy characteristics. So, system architecture and participants. In our architecture, we have 4 participants, namely we have end hosts, endpoints or hosts or edges, which they want to communicate in covert and secure fashion. Basically, they encrypt their packets when they send it to the routers, and when they do so, they use TCP, UDP, TCP IP protocol suite, and they encrypt not only the application payload, rather they encrypt everything, including the header fields of all of the layers. Then, based on the sensitivity of the requirements, we have 2 type of routers. So basically, when those 2 end hosts communicate with each other, they just want to hide everything, including the application payloads and header data from the eavesdroppers that can listen to the channels. However, if they trust the routers, then we have router type 1. Router type 1 basically takes an encrypted packet, decrypts it, sees its header fields, and basically does the forwarding to the next hop. That's why it has those pair of keys which are used for encryption, decryption purposes inside of the router. We have n such routers. This is the case when we trust the routers. However, if endpoints don't trust the routers, even them, and of course they don't trust other entities that can listen to eavesdroppers, that can listen to all of the communication channels, then we have router type routers, RT2. RT2s basically are consisted of 2 entities, namely the forwarding unit and the decryption unit. In the forwarding unit, the forwarding table data, basically only the parts related to headers, such as field headers of all of the layers, such as MAC addresses, IP addresses, TCP UDP ports, are stored in a plain text at the forwarding unit, whereas the output labels or output ports in order, same order, are stored in the decryption unit. Furthermore, the forwarding unit has master keys or key switching keys, has a set of master keys, which basically convert a ciphertext from the domain of one public key to the domain of another public key, so we can decrypt it with the corresponding private key, whether the decryption unit of RT2 has a set of decryption keys. Of course, we have the software-defined networking controller, which basically sends the forwarding table to all of the routers and also their keys, decryption keys, or master key switching keys, and makes public which router has which keys. Okay, what about the attack model? Except for the software-defined networking controller, which is trusted, all of the other entities are assumed to be to the semi-honest or honest but curious model, which means that they follow the protocol, but on the background, they try to infer some data which they're not supposed to. We also assume that eavesdroppers can listen to all of the communication channels between endpoints and routers. And even for RT2, they can listen to the communications between the forwarding units and decryption units. Okay, so let's see the public crypto system that we are going to use it is called somewhat homomorphic encryption, SWHE, and they are based on the hardness of wrinkle WE. Basically, those schemes allow for ciphertext to be performed some operations such as additions and multiplications without decrypting them. Both the plain text and the ciphertext in those schemes, somewhat homomorphic encryption schemes, are polynomials of degree n, and the corresponding coefficients for the plain text are modulo t, while for the ciphertext are modulo q, such that q is much greater than t. If the polynomial degree t and coefficient modulus is t and q are chosen properly, then we can apply CRT, Chinese remainder theorem, which basically enables us a component or index-wise homomorphic SIMD operations over polynomial coefficients. Basically, SIMD means single instructions, multiple data. We will see it in a while. Notation so here we deal only with integers. A simple integer vector is denoted by having an underline v in its name. A plain text is denoted by having underline p in its name in the end. And the ciphertext is denoted by having underline c in its name. Now let's see the operations that somewhat homomorphic schemes allow. So we generate a pair of public key and secret key, private key. If we want to encrypt an integer vector, we just take it and encrypt it with a public key, and it returns the encrypt encode. So basically, we encode it to a plain text and then encrypt it, and the output of this function operation gives me a ciphertext which is encrypted with the public key pk. So we can only decrypt it with the corresponding private key, basically. Sometimes we can omit the public key which was used while encrypting the integer vectors. We can also encode them into a plain text without decrypting them. Adding two plain texts and also adding a plain text and a ciphertext will give me a ciphertext, and it's done in SIMD fashion. Basically, it's illustrated in this figure here. So if I add AC and BC, this is one addition. However, on the background, it's like having n additions, component, index, or slot-wise additions, namely 5 plus 2 is 7, 8 plus 1 is 9, and so on. Similarly, there's another function called add many, which takes a vector of ciphertexts and adds them all in tree-wise manner, basically. Then we can add the ciphertext and the ciphertext, or a ciphertext and a plain text, and the result will always be a ciphertext. It's done in SIMD fashion. It's illustrated in this figure over here. So if I multiply two ciphertexts, this is one multiplication, but on the background, it's like having n multiplication. So this is basically done in SIMD fashion. So 5 multiplied by 2 is 10, 8 multiplied by 1 is 8, and so on till the end. Then we have key switch. Basically, as an input, it takes a ciphertext which is encrypted with the domain of public key A, and a master key re-encryption key, which converts this input, this ciphertext, from the domain of public key A to the domain of public key B. So of course the output will be a ciphertext which is encrypted in the domain of public key B. Basically, we should use the decryption key of the corresponding decryption key of a public key B to decrypt this ciphertext. Furthermore, we can rotate ciphertexts. So basically, rotate is a function which takes a ciphertext, IAC, and rotation R, which is an integer. If R is 0, the rotation is done to the right, otherwise it's done to the left, and it is illustrated here. So this is our ciphertext. If we rotate it by 2, so 5 is in the first index, now it goes in the third index. 8 is second, then goes fourth, and so on. Well, there's 2 and 1, which are in the end, the coefficients in the end of the ciphertext, they go kind of circle around to the beginning. Finally, we can use decode to decode the certain ciphertext, and decrypt and decode to decrypt and then decode the ciphertext into an integer vector. Let's see some other preliminaries, which is the longest prefix match. So basically, if we have a packet, incoming packet, TCP IP packet, and the destination IP address looks like this, then in the forwarding table, we are going to see a match. Okay, so there is a match. The output port is 2. But if you look furthermore, there's another match, and this one is longer than the first one. Here, the output port is 1. Basically, we're going to use the one with the longest prefix match to forward the table. Generalized forwarding is software-defined networking. Unlike the traditional forwarding protocols, which used only destination IP addresses to forward packets from input to output in routers, here in SDN, to do forwarding, we use multiple fields, such as source and destination IP addresses, MAC addresses, TCP, UDP ports, and it's given over here. Okay, now let's start with our secure building blocks. Basically, everywhere where we mention encryption, we mean somewhat homomorphic encryption, and they allow SIMD operations in the way that we just explained. So our first secure building block is secure SIMD bitstream batch. It's given in this pseudocode and illustrated with this picture. Basically, we take a ciphertext, which is an encoded encrypted bit stream of n bits, and a plain text, which also can be ciphertext also, which is an encoded bitstream plain text of n bits, and we want to see where they match. How do we do that? Well, we firstly subtract them in SIMD fashion, and then we multiply them with random number, which shouldn't be 0. So let's see, 0 minus 0 is 0, 0 multiplied by 23 is 0. Basically, this means that in the result, in the corresponding slot, if we have 0, that means that in AC, the inputs, the corresponding bit match are the same. Or 0 minus 1, minus 1, minus 1 multiplied by minus 941 is 941. If this is not 0, this means that they don't match. So this is the resulting vector. Okay, ciphertext permutation, secure ciphertext permutation. It has an input. It takes an encoded and encrypted bit stream of n bits, and also a vector KV, which consists of m elements and gives the rotation index for each of the m slots inside of the blocks. Basically, here it's illustrated with m3. So the block size is 3, and the vector KV is 2, minus 1, and minus 1. Basically, that means the first element goes 2 to the right inside of the same block and becomes the third one. The second one, minus 1, goes 1 to the left. The third one goes 1 to the left. And this is done for all of the blocks of the ciphertext. How do we do that? It's illustrated in this figure. So basically, for all of the elements, m elements, we just construct a mask. So this mask has 1 for the first element of each block, has 1 in the first slot of each block. So we multiply the input with the mask. So basically, we get A1 here and the first element of each block. Then we rotate it by 2 to the right, and here it comes. So A1 goes to its place, the third place, from the first to the second. Similarly, A2, we construct a mask which for each block in the second mask, in the second slot for each block has 1. We multiply the input with the mask, the second mask. And then you see it should be rotated by minus 1 to the left by 1. So A2 multiply this guy and then rotated by 1 to the left, we go here. So A2 goes to its spot. Similarly, what happens with A3 and mask 3. And then we just add those up and we get the desired result. So basically, A1 goes to the third spot. So rotated to 2 by 2 to the right. A2 and A3 are rotated by 1 to the left. Let's see secure SIMD prefix match. It's given in this pseudocode. It takes two inputs, AC and BP. They are cipher. One is the first is ciphertext, AC, and the second one is plain text, but they can be both ciphertexts. Now, the interesting part here is that in bitstream 1 and bitstream 2, we want to see the exact match of them, whether they exactly match or not. However, in bitstream 2 and bitstream 3, we just want to check the longest prefix match. Okay, that's why here in bitstream 2, I have a wildcard in the last slot of those 4 bits. And here in bitstream 3, I have 2 wildcards. Basically, I want to check whether the first 2 bits match with the corresponding bits. So, as you see here, we just, in third line, we just use secure match, which we explained, which is basically AC minus BP multiplied by R. But the interesting thing is that, as I explained in bitstream 2, bitstream 3, we take care about longest prefix match, and bitstream 1 and bitstream 4 only about exact bitstream match. That's why RP is constructed in the following manner. Wherever we have a wildcard for the longest prefix match bitstreams, we have zeros. And when we care about the exact bitstream match, they are non-zero random numbers. So we just subtract AC and BP, which are our inputs, multiply it with a random number, and get this result. As you see here, in bitstream 1, everything is 0 because those bitstream match. Bitstream 4, everything is not 0 because the first 2 bits are not 0 because they don't match. Whereas for bitstream 2 and bitstream 3, everything is 0 because they match. But the issue is not whether they match or not. We want to see what is the longest prefix match of those 2. That's why we're going to construct a mask, which for the bit streams where we care about the exact match has everything 0. Whereas for the bit streams where we care about the longest prefix match, we put ones in those bit slots, bit indexes, which don't have a wildcard, and when we have a wildcard, we put 0. Okay, so here we have the first 3 bit, 1 star, 1 wildcard, which is 0. Here in bitstream 2, we have 2 wildcards, 2 zeros. Now this one's vector is subtracted with the result that we just explained, and we get this guy. So basically, here in the result, we have 0. Let's just see those longest prefix matches. In bitstream 2, we have 3 ones. In bitstream 3, we have 2 ones, meaning that the first stream has the longest prefix match. Whereas for the bitstream 1 and bitstream 4, where we cared about the exact match, we have all zeros for bitstream 1, meaning the bits exactly match. Whereas for bitstream 2, we have 2 non-zero numbers, meaning that in 2 bits they don't match. If we want to hide which bits they don't match, we just execute the secure ciphertext permutation protocol, and we should hide them because, MAC addresses and UDP, TCP ports they use exact bit stream match. That's why we want to hide those MAC addresses, so we permute the order of the bits. But in the end, we're going to see bitstream 1 exactly match, bitstream 4, in 2 bits they don't match. Bitstream 2, bitstream 3, the longest prefix matches belongs to bitstream 2. They all match, both of them, 2 and 3. But the first one has 3 ones, the second one has 2 ones. So basically, the winner is bitstream 2. If we are dealing with longest prefix match, and if there is a number in the bitstream where we care about longest prefix match, and that number is not 0 or 1, that means that we don't have a bitstream. We don't have a bitstream match at all. Finally, why do we care about this? Well, secure prefix match deals with both bitstream matches and longest prefix matches, which this is suitable for prefix matches for TCP, UDP ports, and MAC addresses, and longest prefix matches for IP addresses, in the way that we just explained. Finally, the last building block, secure ciphertext replication. It takes an input which has these slots, which are non-zeros, everything's zeros, and we want to replicate it by R. How do we do it? Well, this D is rotated by, the input is rotated by D, so we get this one, then those are added up to get this intermediate result, then it's rotated by 2D, those two are added up, and finally, we have this guy, which is the input, basically replicated by 4 times. Now let's see our first secure routing version, secure routing or version 1 protocol. A kind reminder that wrinkle W schemes that we just explained, or somewhat homomorphic encryption schemes, are probabilistic in nature. That means if we take the same ciphertext and we encrypt it different times, in all of those times we're going to get different ciphertexts. This is due to the probabilistic encryption nature of the explained schemes. A kind reminder to our system architecture. In secure routing version 1, we deal with type 1 of routers. So basically we trust the routers. We can reveal to the routers our data. So what happens? An endpoint takes an input packet, payloads, all headers. It's going to encrypt it with one of the keys, public keys, for which the first hop router, let's say this one, has decryption key, and is going to send it to the router. Then the router is going to decrypt the packet, and based on the data and the forwarding table that it has, is going to determine the output port. Then it's going to check whether the next hop, perhaps this is the next hop, has the same decryption key that the first one has. If it's the case, then with this input packet is just going to be kind of refreshed by adding zeros, right? Due to the probabilistic nature of the wrinkle WE schemes. If I add zeros, I'm going to get another ciphertext. Okay, otherwise, if that's not the case, then I'm just going to re-encrypt the packet with one of the keys that the next hop has, and I'm going to send it to the next hop. And this is repeated for n times, or how many times for each hop, up until it reaches the destination. Okay, so in this scenario, we don't trust the others that listen to the channels, but we trust to the routers. What if we don't trust to the routers? Well, that's why we are dealing with router version 2, where we had the decryption unit and the forwarding unit. And again, let's not forget that we are dealing with the probabilistic encryption nature of the underlying encryption schemes. And also in the first version and in this second version also, we assume that the routers deal with a lot of traffic. So what happens? So this is our forwarding table. In the forwarding unit, we just have, for each row, we just have those data, MAC addresses, headers basically, which are stored in a plain text at the forwarding unit, whereas the corresponding ports are stored in the decryption unit as in order, are stored in the forwarding unit in that order as an integer vector. Okay, so this is the forwarding table. From this forwarding table, this is the forwarding plain text, which deals only with the forwarding data, whereas the labels are in the decryption unit, also in order. So you have row 1 here of the forwarding table and the corresponding output port 3 in this label vector. This is row J and the corresponding output of row J, and so on. Now what happens? Again, an end host is going to encrypt its data and send it to the first hop to the router. So this is the packet. And this is, by the way, what happens in one router, not multiple one. In one router, a certain router takes an input packet, and after it takes this input packet, it's going to replicate it in this way. Okay, so maybe it takes only the header of the packet is going to replicate in this way with the first line. In the second line, we are going to apply the secure prefix match that we just explained. Of course, here we care about in some bit streams, we care about the longest prefix match. In some of the other, we care about the exact match. Everything is taken care in this line. And after we apply the secure prefix match, we set the result of the decryption unit. Now the decryption unit is going to decrypt it and find, based on the output of the secure prefix match, which is the corresponding output level for the packet, and it's going to send that output level again to the forwarding unit. Now the forwarding unit will see the output level, knows the next hop, and sees whether there's the same key, whereas the next hop has the same decryption key that the input packet came with. If that's the case, it's just going to refresh it with zeros. Otherwise, by adding zeros basically, and forwards it. Otherwise, it's going to use the key switch to convert the input packet to input packet ciphertext from the domain of the public key. It was encrypted into one of the public keys of the next hop and is going to send it to the next router. Now, this is only for one router. For multiple routers, of course, we're just going to apply secure generalized forwarding for n times up until it's routed or forwarded from the source to destination. An improvement here is, in order to avoid the costly key switch operation, all of the routers can have the same decryption key, so key switch is not needed to be done. Okay, here is we give the theoretical analysis or homomorphic computational complexity. This is the experimental environment. Results are given here. And this is it. Basically, our screens are also proven to be secure under the semi-honest model. And this is the discussions where we propose several secure building blocks. On top of them, we built a couple of secure and private communication protocols. We show that they are secure and they have good computation and communication efficiency. In the future, we also plan to add extra characteristics of the TCP/IP protocol stacks, namely secure and private cyclic redundancy check evaluation, flow and conjunction control, network address translator, and so on. Thank you for your attention and looking forward to your questions.